Hi, my name is Matt Holliday and welcome back to my class on programming in Go. So now I'm going to talk about some odds and ends. Specifically, I want to talk about enumerated types in Go because Go doesn't have an enumerated type, but it sort of does using a particular paradigm. I want to talk about variable argument lists, and I want to talk a little bit about bitwise operators and short integers. So I'll start with enumerated types. Now, there are some languages where the enumerated type is a specific thing in the language. There's a keyword like enum. And Go doesn't have that. But Go does have a mechanism for producing more or less the same thing. And I'm going to show you 3 examples on the slides to try to illustrate that. And they all have something in common. And what they have in common is a very interesting Go operator called iota. Okay? Iota is an idea that was actually taken from a very old language called APL, but it's a thing that magically increments. Okay? It's one of the few magic things in Go. So if I look at this example, and we do this by having a constant block. So we have a bunch of constants in a block surrounded by parentheses. And we start the first one with iota. And the next one, each one subsequently, they take the next value. Okay? Iota always starts at 0. Okay? So if I look at this, and one more thing, and that is I've created a particular type. So to separate these enumerated values from ordinary integers, I've given a type here, shoe. Its underlying type is int, so we'll represent them as numbers, but shoes will be distinct from integers in many cases. Right? So the tennis shoe will have the value 0, and the dress shoe will have the value 1, the sandal 2, and the clog 3. Because once I've used iota on the first line, I've given the type an iota, that carries down all the way down to the end of this constant block. Okay? And so those values just get what they get. Now that's good as it goes, and if that's all that were there, it would be kind of useful, but we can put expressions around iota, and we can do a lot more with it. So let me show you the next example. And the next example will look a lot more like what goes on in other programs that need to do bit flags. Okay? I've got an expression. And my expression, and we haven't talked about the shift operator yet, okay? So maybe this is a little premature, right? The bit shift operator, if I have a bit here, right, well, it moves it over 1. But in this case, it's going to move it over as many times as iota says to move it over. And effectively, what they're going to do, what it does, is it's going to create powers of 2. Because iota starts at 0, which means in the first case, I end up with a 1 bit. And in the second case, the value 2 and the 4 and the 8 and the 16. Because what I'm doing successively here, right, the first one has a 1 in the low order bit. But the next one, I've shifted that bit over 1. So now it's a binary 1, 0. Well, that's a 2. And now I come along and for the next constant, I shift it over another 1. And so on. Right? And that's how I get these successive values. They represent different bits in a word. And we'll see how that's used in a second. Okay. But the expressions can be yet more complicated. Right? Now, the other thing I can do is I can ignore the first value by putting an underscore. So underscore equals iota, iota gets 0. And then I redo this expression with something a little more complicated. All right, and I use iota again, but it's not going to start over at 0. All right, it's just allowing me to redefine this expression. So the first thing, 0, the 0 value gets used up by the underscore constant. It just disappears. I can ignore 0. So all of my numbers are going to be starting at 1, 2, 3. Well, what if I get in this expression, if iota is 1, right? Well, I get 1 shifted 10, and that's the equivalent of 2 to the 10th, right? And the next one is 2 to the 20th, and so on, right? Until I get down to the bottom, and this one will be 2 to the 60th, which is a really big number. So that's about all I have to say about enumerated types. You can do clever things with them, provided you can come up with a useful expression to capture iota and do things with it. And again, they work in a constant block. If I had another constant block after this one, right, with iota, iota starts over again at 0. That's just a trick. So iota is one of the few magical things in Go. Now, we've already seen plenty of examples of variable argument lists because everywhere where we do printing, we've been able to pass in different numbers of arguments. So there's a mechanism for doing that. And in the playground, I have this simple example. Now, I want to point out some things about syntax. The first is we have a new operator. It's 3 dots together, okay? Dot, dot, dot. But they're together with no space in between them. When I apply that to the type of a parameter, what I'm saying is it's a variable number of items, right? Now, there is a catch, right? Can I do this? And the answer is no. Only the last parameter in the parameter list can be variable, which kind of makes sense because here's the thing. If I did this, particularly 2 variable length list of integers, how would I ever know which ones belong to the first parameter and which ones to the second? Okay. And the dot, dot, dot in a sense is treated a little differently. I can't do this because that would mean, again, the same thing as I just wrote a second ago, right? This doesn't mean x is an int and nums is a variable number of ints, okay? And so if I want one int followed by some number of ints, I would have to do what you see here, okay? Well, I'm not going to do that. What I'm going to do is create a sum function, and my function will sum up however many integers there are. Now, this is nice. Again, my total starts at 0 because that's the default value, all right? And range, operating on this variable argument list, works exactly the same way as it works for a slice, okay? So inside this function, nums can be treated exactly the same as a slice event in terms of iterating over it. And if there aren't any, then the for loop doesn't iterate at all. And then we just return 0. So here's my first case, right? What will this do, right? When I run this program, the first one returns 0 because there wasn't anything to add up, so it just returned total with its default value, right? In the second case, it added 1 to 0, got 1. In the third case, it added all these numbers up. Now, you're going to ask, so if nums can be treated like a slice, can we pass a slice to it? So let's try that. Where s is going to be a slice of int. All right, and we'll get rid of this one for a second. Okay, so I created a slice of int s and I want to pass it into sum. And the answer is that's not going to work. Okay, but there's a way around this. Now, we're going to put 3 dots after the actual parameter. Remember, the formal parameter is when I define a function. So nums is a formal parameter. When I define a function, if it's going to be variable, the 3 dots go in front of the type. When I call a function with an actual parameter, that's a slice, that I want to use in a variable argument list, then I put 3 dots after the actual parameter to unpack it, right? And this just says, hey, take the slice apart and fill it into these values of nums, okay? Now, it's not that dumb at runtime, right? It's a syntactic device that says, I can pass a slice as a variable number of integers. Why not? It is. So let's try running that. And I get the answer I expect, okay? So 3 dots in front of the type when you define the function, but only the last parameter, all right? But if I need to pass a slice for those variable arguments, then 3 dots after. Now, there's an interesting side effect here also, right? If you remember the append function, right? Append, right? I can append something to s. And normally I would append like 1 to s. So let's just do that really quick, right? And add it up, okay? What if I want to append a slice here? Well, if I put s there again, okay, it's not going to work because it wants an individual integer, but append takes a variable argument list. So I can actually append right there, and I get s twice because it takes this s, unpacks it as a list of 1, 2, 3, 4, and appends them to s, And now my S has 2 complete copies. In fact, if I were to print that, right, if I were to print what it looks like before we do the sum, 1, 2, 3, 4, 1, 2, 3, 4. Okay, so in case you haven't noticed it, we probably haven't used it this way, but append takes a variable list of things to append to the slice, and I can actually unpack another slice into those variable arguments. So I want to talk about my third topic now, and these are integers of unusual size. Okay, because I said in most of our programs, and you've seen this, we almost always use the type int. All right? And on almost all the machines you're going to work with now, it's a 64-bit int. It's huge. We can almost number all the stars in the sky with it. Okay? There's a variation called uint, which is unsigned, which we might use every once in a while. It's not that common. Okay? But sometimes we need integers of a specific size. That's going to be most commonly unsigned. And here's the example. This structure represents the fields of a TCP packet header. Okay? Which you're not going to find that in Go very easily because normally that's handled by the operating system kernel underneath the Go program. And so you don't typically see an actual packet with a header in a Go program. But if I wanted to describe the header of a TCP packet, here's one way to do it, right? Because these fields have different sizes. And, you know, if you had a diagram of this protocol, it would probably show like bits 0 to 32, and it would show this first thing being 2 parts, and then it would show this whole thing for the sequence number, and this whole thing for the act number, and, you know, and then it would start showing little bits of things, right? And so you'd see these various fields in the header, and they would map to different things like, you know, the flags and offsets and so on. Okay? That's what you'd need to do in order to pick out the particular values out of the header. You'd define it with these short integers. So I'm in the playground with some bitwise operators, which I'll explain, and the formatting unfortunately makes them hard to see. So let me reformat these guys just a little bit. Okay. Now, 0xXFFF is a hexadecimal constant. It's going to be all ones. Okay. 0b something is a binary constant, and the digits can only be 0 and 1 after that. So this represents 4 1-bits. Now, there are some operators here. This is the and not operator. Okay. The and operator. The not operator, which operates by itself. In other words, it's a unary operator. It just applies to the value, right? And then the or and XOR, right? So the caret does double duty when the caret here actually triple duty. Here the caret means and not, although actually it does exactly the same thing as that. So it doesn't matter, all right? It's just a convenience to write it that way. Here it's a unary operator meaning not, and here it's a binary operating meaning XOR. Binary in the sense of it's between 2 operands. So let's run this and look at some of the bit patterns that come out of it. Okay. So here's A, and I said A had all the bits turned on. It does. All right. The first expression with the and not turns off the low 4 bits. In other words, it's masking off or removing the 4 bits at the bottom, whereas the regular and operator, okay, removes all the bits except the ones at the bottom. And that's really easy to see then with this pattern, right? So and not, right, zeroes out the low 4 bits, but the and only allows the lower 4 bits to come through, right? If I change this value to be something different, let's run that again real quick. Okay. Notice now, even though I've done an and with 4 bits, only 3 of these bits are, 3 of these bits are ones, because only 3 of those bits were ones in the original word. So now let's look at what happens with B and these remaining operators, right? So here's B, and if we look at not B, the bits are just flipped over, right? A 0 becomes a 1 becomes a 0. Okay? An OR says, hey, if the bit was 0 or 1, it's now going to be 1. So this OR expression here forces the low 4 bits to be 1 no matter what. Right? Whether they were 1 before or not, they are 1 now. The last one, XOR, is kind of like OR with a special rule. if both bits were 1, then the actual result is 0, which is a little weird. But we see that because if we look at the low 4 bits, 1, 0, 0, 1, we end up with the opposite just for those 4 bits. Because the 1 there and the 1 here in this constant combine to create a 0. Now, if I made that 0, 1, 1, 1 and run this, then we get 1, 1, 1, 0 because we have a 1 here and a 0 here, and then the other 3 here are 1s, and so they do their usual thing, and this low order bit that was a 1 becomes a 0. Okay? And that's probably as much as I want to say. These are low-level operators for doing bit fiddling for people who do things like protocols or, encoding and decoding ASN.1 or protobufs. If you were writing the protobufs code, you might fiddle with this kind of stuff. So I want to combine a couple things now to show you a practical application. Let's remember, a couple slides ago, we had our definition of the TCP header. And one of those fields is flags, right? It represents a bunch of 1-bit flags. Okay, great. Well, how do we deal with that? Well, we can define a set of constants that represent the different flags. And again, by using an expression like this, each one of these flags refers to a different bit position, right, in this flag word, right? So the first one is the low order bit, and the next one is the bit after that, and so on. Great. So we can combine that and these low-level operators. A TCP packet is a SYN-ACK packet, which is part of the sequence how you set up a TCP connection if the SYN flag and the ACK flag are both set at the same time, right? Well, how do we do that? Well, we take those 2 bits and OR them together, which effectively means we have something that looks like, some number of zeros, 1, 1, 0, okay? And then we use the AND operator with the flags, so that only those 2 bits matter. And then we look at the result and say, is it the same as having those 2 bits on? So we take that flag pattern, and we take the actual flags, and we ask ourselves, does the result include having these 2 bits set on? All right, so this is this, and the result, the flags would be this, and we take and we look at the result to see if it matches this. And if it does, both of the flags were turned on. All right, so that's a typical application of these operators. I'm going to bounce back to the playground because there's another set of bitwise operators I want to mention very briefly, and those are the shift operators. Now, for a few of you, you may know there's arithmetic and logical shifts, and without explaining it a whole lot, I'm just going to say these are logical. All right, so the shift operator takes the bits and pushes them over. And we'll see this in effect, right? So I'm going to have some numbers up here, and we're going to see what happens when I move them around. So the first one of these was A, right? And A is 1024, all right, which means it has this 10th bit over here set. And what happens when I make it shift over 3 bits is literally this whole number gets pushed to the left, if you will. Zeros are introduced over here, bits on the left disappear, and this 1 bit appears to move 3 spaces to the left. Okay? Actually, the whole thing will move, and we'll see that. Now, what happens if I move it 13 to the left? And the answer is, I get 0 because I only had the 1 bit, and it just kept moving off to the left and disappeared. Okay? So if I shift my number too many places, I'll end up with 0 bits because, in a sense, I'm shifting 0 bits in from the right, and I'm shifting my real bits off to the left. And I just shifted my bits so far off to the left that there's nothing left but zeros. Let's look at B here. Okay, B is 255, so it's 8 bits that are all set, all 8 low bits are set. I'm going to shift that 2 bits one way, and what happens is all of these 8 bits move over 2 spaces, and I get 2 new 0 bits over here on the right. I'm going to shift it now to the other way, the same B, right? It's this B, but I shift it 2 over. So what happens is I'm shifting zeros in from the left now. and I'm shifting real bits off to the right. And so the 8 bits that were set, I only have 6 of them left because 2 of them just dropped off the right, and zeros came in from the left to fill in. Right? Now, I want to show one more of these because I said this is logical, right? Logical, right? And my value C, if we looked at it, and maybe we should do that, if I print C and look at it, right? C has the high 8 bits are set. I'm going to shift it to the right. Okay, again, zeros come in from the left, and all my 8 bits move over 2 spaces to the right. That's why it's called logical. There is another method that Go does not support called arithmetic shift, where if your high bit is set, you shift in 1 bits from the left. Go doesn't do that. Okay, so regardless of how we shift, 0 bits come in from one side and bits move off to the other side. Okay, so I'm not going to show those anymore. Again, they're useful for low-level programming. Now I want to talk about what can go wrong with small integers. This is not specific to Go. Any programming language that allows you to have small integers like 8-bit integers and 16-bit integers, or really integers of any fixed size, is going to have certain weird behaviors. Okay? The first weird behavior I want to talk about is what happens when you shorten an integer. Okay? So I have a couple of values up here. Right now, they're 32-bit integers, and they're a little big. All right? In fact, what I should do before I do anything else is I should probably just print. Well, actually, I'm doing that. Never mind. Yeah, we'll just print A and B by themselves. All right, give me 1 second here. We'll print A and B, right? So, in a 32-bit integer, they fit, okay? What happens when I put them into a 16-bit integer? That's the important question here. And so I'm taking the results of shrinking these things down, right? And showing you what they look like as bits, before and after, and then the final integer value. And you're going to look at this and say, hey, wait a second, because one of these came out negative. And what's actually happening is that when we move these things from a 32-bit integer to a 16-bit integer, we're just throwing away the high 16 bits. So if I look at this number, right, all of these bits here go away. Well, they don't matter because they're all zeros. Okay, actually all of those bits, sorry. Okay, now when I do the other number, the same sort of thing happens. All those bits go away, and what I'm left with is this group of bits over here. Those are the 16 bits that remain from taking the 32-bit integer and shoving it into a 16-bit integer. And if I interpret that as a signed number, it's going to be negative. Because, I'm just going to tell you, the way computers represent numbers, if the high bit right here, this first 1 bit down here, if that's a 1, the number is negative. Okay? So these numbers got turned into something very weird by being taken from 32 bits into 16. This is why Go does not allow you to just mix different sizes of integers. All right? Other languages like C and C++, a lot of languages, allow you to take integers of different sizes, and maybe some are signed and some are unsigned, and just do math on them. And, a lot of times it sort of just works, and every once in a while, really weird things happen. And Go has decided we're not going to let the weird things happen unless you tell them to happen. So if you want to mix a 32-bit integer and a 16-bit integer, you're going to have to decide how to do it, right? The right answer is probably to make the 16-bit one grow to 32 and then do the addition. But you're going to have to acknowledge what you're doing and think about what the consequences are of how these numbers are interpreted. And again, most of the time we just use int. Why? It's 64 bits. It's so big, you can't count that high in your lifetime. And we just don't have to worry about some of these problems. It's that big. Okay, I have one more little piece because I want to talk about short signed integers. They have a weird behavior because signed integers, the way the computer represents them is something called 2's complement. Okay? 2's complement ensures that we only have 1 0. There was an earlier model called 1's complement where you simply, to make the negative of a number, you flip the bits. The problem with that approach is you have 2 0 values, a -0 and a +0 in a sense, which mathematically is weird because, of course, 0 is not a signed number. All modern computers use 2's complement. And so if you think about like an 8-bit pattern, okay, it holds 255 values, 2 to the power of 8. If it's an unsigned thing, then the values are literally 0 to 255. Did I say 256 values, 0 to 255. What happens when I represent signed integers? Well, it represents 0 to 127 and -1 to -128. Okay? There's one more negative number than positive number, and weird things can happen. Now, I'm going to start with this in 16 bits, right? Because nothing weird is going to happen. I have my number -128. I'm going to multiply it by -1 or divide it by -1 and get +128. That's fine. I'm going to add and subtract 1. That gives me -127 or -129. And that's all mathematically sound. That's exactly what we would expect if we were doing this on a piece of paper. Great. The bit patterns are a little interesting. Notice again, every number that's negative, the high bits are set to 1s. Okay? Now, and if I do this with -1, I get something very similar, right? -1, +1, +1, 0, -2. Now notice, again, +1 is this case of 1 bit and the rest are zeros. Okay? But -1, it's all, the bits are all set. That's how you represent -1 in a signed integer. Great. Now, I want to take this into the world of 8 bits because now we're going to start seeing something weird in a second. I'm going to run it again with 8-bit integers and I'm going to get what I expected. Now I've got a bunch of zeros here because I was printing this with leading zeros in my printf. All right, I could change them all to 2 and maybe I should because that would better represent what we're actually looking at. Okay, -1, fine. What happens when I try -128? Now remember, we're in an 8-bit integer. -128 is the most negative number you can have in this integer. And unfortunately, weird stuff happens. Okay? Because -128, okay, if I make it negative by dividing or multiplying by 1, it remains negative. Okay? If I add 1, it behaves normally and gives me -127. But if I subtract 1, it behaves abnormally and gives me a +127. Again, this is not specific to Go. It happens in any language that allows you to have short integers. Right? If I do this with -1, it's not really a problem. Okay? If I do it with -127, it's mostly not a problem. Actually, that all behaves right. But -128 behaves wrong because it's this weird number that represents a negative number and there's no positive number to match it, and so weird things happen with the math. Now, signed 8-bit integers are pretty rare. Signed 16-bit integers actually have a use. If you open up a WAV file with music, it's going to have a bunch of sound samples. They're 16-bit signed integers. And if you want to do math on your WAV file, you might end up messing with them. And this is a warning that they don't, the most negative number behaves weird. Again, in a normal Go program, we don't use sized integers. We just use int. And it has so many numbers, the most negative number is some quantity that we'll never deal with. Not normally. So we just don't care about it. But if you have to work with smaller integers, then you have to start caring about it. And again, this is why Go says, hey, if you're going to deal with these things, you really got to think about what you're doing. And then we have a surprise, okay? Go has a Goto statement. Now, once upon a time when I was very young, Okay, I learned languages like Fortran 4 and early versions of BASIC. And the only way you had of controlling your program was either something like a for loop, okay, which was very, very simple, much less powerful than a modern for loop, and essentially go-tos. And we wrote something that was called spaghetti code. And people didn't like it, and they were right not to like it. And somebody finally wrote a paper called Goto Considered Harmful, very controversial, but got people to decide that in most cases, programming with go-tos is bad. And so there are a lot of languages now that don't have a go-to statement. Go does, okay, it's a carryover from C, and arguably you don't need it, but every once in a while it's handy. And I want to show one particular case, and I'm doing this because somebody challenged me. Show me a case where goto is useful and safe. And here's my case, okay? I've got a piece of code, and literally this is a piece of code programming, I'm looking at a WAV file, and I'm ready to read a header called the format header. Well, unfortunately, sometimes when people make WAV files, they pad them, and right before the format header, they throw in some headers, one or more headers called junk headers. Okay, literally JNK in the header, right? So I'm reading along here, and I go to read my header, and if it turns out to be a junk header, then I'm going to do some logic, and the little bit of logic is left out of here. I basically need to figure out how big it is and skip over it. And then I'm just going to go right back to where I was and try to read the format header again. Okay? It's sort of an exceptional process. I get down here and there's this junk header, so skip the junk header, go back, and start the process over again. Now, I could have done this with loops. I could have even done this possibly with a recursive function call. I don't think any of them would be as clean. I think this is very simple and clean and obvious what it's doing, and it's safe. And so this is a case where goto maybe isn't harmful, maybe it's practical. Okay, I'll let you decide that. So that's a little section on odds and ends. We talked about how Go does enumerated types, how to do variable argument lists, which are kind of useful, mostly for the standard library. We talked a bit about short integers and bitwise operators, which I didn't want to talk about in the beginning because they're kind of specialized. And then as a surprise, we finished up with an example of goto. Okay? These are the odds and ends.